chime, that record chime to come on. There it is. All right, you guys, we're back in here, BC Calc kids. We're back here in the rectangular approximation method, where you use a series of rectangles to approximate the area under a curve. So the general procedure is to draw the graph of the function on a closed interval from A to B. And notice if it goes from, 2 to 7, that it would be 7 minus 2 units wide. This just refers to how wide it is. And then you have to decide how many subintervals to use. On your test, they will tell you. They will say use 5 intervals, use 4 intervals, use 3 intervals, whatever. The bigger the value of n, the more rectangles that you have, and then the more accurate would be the approximation. And notice, since this is the width of the entire interval, and we're dividing it into n equal intervals, each subinterval is of this width here, okay? And so this formula is just a matter of, well, how wide is it divided by how many there are, okay? And then you have to decide if you're going to use the left, right, left, middle, or right, and then finally calculate those areas and add them up, okay? So as an example, I've already drawn the graph for you using Desmos. This is the curve y equals 4 plus sine x. I want to make sure I'm not degrees mode. I want to make sure I am in radians mode for this. And let's get this in here. What is it? 4 plus the sine of x. Like, whoops, that was weird. 4 plus the sine of x, like so. Excuse me. I know how unacceptable it is to cough or sneeze these days. Okay, so we have 4 plus sine of x. Okay, and we're going from 2 to 8, and we want 3 subintervals. And so you think, oh gosh, 2 and 8 are even, and we're dividing by 3. But remember, this is A, and this is B. And so the entire width is 8 minus 2, or 6 units wide. So from here to here is 6 units wide. And then we're doing 3 subintervals. So if you do this divided by 3, by n, you do b minus a all over n, right? You end up with this, or 2 per rectangle. And so the first rectangle is going to be 2 units wide. The second rectangle is going to be 2 units wide. And then the third rectangle is going to be 2 units wide. So that looks pretty good. And then it says MRAM, okay, the midpoint of each of these rectangles. So that means the middle of each x value, not the y values, the x values. And so if we look here, this first rectangle is going to go from 2 to 4. The second rectangle is going to go from 4 to 6. And the third rectangle will go from 6 to 8. And so we need to simply pick the midpoint there. That would be 3. This one is 5. And this one is 7. Okay, and so basically what I need to do is calculate these areas. This area here, it says midpoint, so I'll go there. At 5, this is the value of the function, so I'll go there. And then this one is at 7, so I will go here. Okay, and so then the question becomes, well, how do these areas above this rectangle compare to the areas below the rectangle? Do those kind of even out? And they usually will. Okay. So anyhow, let's work that, not exactly, but they come pretty close, okay? And so we just need to calculate each area. So we'll call this area 1, area 2, and area 3, okay? You're expected to do 3 decimal places of accuracy. So what I would do is calculate everything to 4 or 5 decimal places and then do your rounding at the end, okay? So area 1 is equal to the base, this is 2 units wide, times the function evaluated at 3, that midpoint value. So that would be 4 plus the sine of 3. That is the that's the y value here at 3. Okay. And then the next rectangle is 2 units wide, and I'm going to evaluate that at this function evaluated at 5. So that would be 4 plus the sine of 5. And then the last rectangle would be 2 units wide times 4 plus the sine of, in this case, the midpoint is at 7, the sine of 7. Okay. All right. And I'm thinking in terms of, adding that all into the calculator. Let's see. Gosh, I could take out this common factor of 2, and then I would have inside here 4 plus 4 plus 4, which is 12. Plus the sine of 3, plus the sine of 5, plus the sine of 7, right? I'm just trying to think in terms of computing this you know, what is the easiest way to handle doing that calculation, right? I take out the GCF of 2, and I just have 4 plus sine 3, 4 plus sine 5, and 4 plus sine 7. 4 plus 4 plus 4 is 12, sine 3, sine 5, sine 7. So let's crank that out. So we do 2 times the quantity of 12 plus the sine of 3 plus the sine of 5 plus the sine of 7, close parentheses. And there I have it. And so there I have an area of 23.678336 and so on. We round to the 3 decimal places. And this is, what do you say? 5 and above, give it a shove. 4 and below, let it go, right? So you have 23.678 square units. Okay. All righty, now you're in calculus, okay? So let's talk about this, all right? If we call this function f of x 4 plus sine x, 4 plus the sine of x, what we want to do is calculate capital F of x, the antiderivative of this. And you guys are able to do that. I wish we were in class now so I could call on you and ask you what function has that derivative. I think most of you recognize it's 4x. And then it gets a little dicey with the sine and a cosine. You probably know it's a cosine of x, and then you always have to worry about that minus sign. Is it plus cosine of x? Is it minus sine of x? The derivative of the cosine is minus sine of x, and so I need to put in a negative sign here to make this thing work out. The derivative of the cosine is minus sine of x, so the double negative gives me that plus, okay? And then, of course, an antiderivative of this function would have some arbitrary constant here. This can get you in a little bit of trouble notation-wise, so it might help to spell it out like so people recognize that that constant is separate from the argument of the cosine function, okay? All right, and then what we're going to do is, to get this area, we're going to evaluate capital function f at the right edge, 8, and we're going to subtract capital F of x at the left edge, 2. Okay, and so basically the area under the curve, the exact answer would be, you plug an 8 in here. So that would be 4 times 8, 32, minus the cosine of 8 plus c, and then minus, and let me do this again, but this time I'm going to plug in a 2. So that would be 8 minus the cosine of 2 plus c, like so. Okay, I'm sorry, my work is kind of jamming together here. Okay, and then if you look at that, you end up with the area of this is 32 minus the cosine of 8 radians plus c minus 8 plus the cosine of 2 minus c. Okay, and if you do that, you'll see that the c's go out, and I basically have 32 cosine of 8 and then minus 8, and then plus the cosine of 2. And so I'm curious, I bet I'll get something pretty close to 23.678. Let's give that a whirl and see how that works out. 32 times the cosine of 8 radians minus 8 plus the cosine of 2. Okay, and let's see what we end up with here. Okay, totally different answer. Okay, clearly I messed something up in there pretty badly. Don't know what I did. It's pretty crazy. Am I in the right mode? I should be in degrees mode. Degrees, no, I'm sorry, radians mode. I want to be in radians mode. Well, I'll be darned. Well, I don't know what I did. 4x minus the cosine of x. Yeah, that's really strange. Put an 8 in there. So 32 minus cosine of 8 plus c, and then minus, put a 2 in there, 8 minus the cosine of 2. Yeah, that looks absolutely correct to me. Okay, I'm going to stop this video, and we will try again. All right, darn it. All right, let's stop.